Today we're going to look at one of the October-November 2024 past papers. Now the first question gives us a list of chemical and physical processes which are labeled A to H. Now let's quickly go through each of these and just explain what they are. So we're going to start with combustion. Now combustion is a process where a substance reacts with oxygen to produce usually carbon dioxide and water. And this then releases energy in the form of either heat or light. So we get two types of combustion. We get complete combustion and then also incomplete combustion. Now, complete combustion is when a substance reacts with a sufficient amount of oxygen to be able to produce carbon dioxide and water. Whereas incomplete combustion is where this substance reacts with an inefficient amount of oxygen, which then produces carbon monoxide and water. Now, both these reactions release energy, meaning that both of them are exothermic. So their change in enthalpy will be negative. Next, we'll have a look at diffusion, and this is one of the movement of particles. Remember, we get diffusion and osmosis. Now, diffusion is the random movement of particles due to kinetic energy. So let's say that we put down a box that's filled with particles. These particles will move randomly, bumping into each other due to kinetic energy, and then spread evenly to fill the available space. Diffusion can also be defined as the movement from a high concentration to a low concentration. Next is melting, and this is a physical process that occurs. It happens in almost all elements. Now, we can imagine melting and all other physical changes as a graph. So we'll draw a graph of temperature against time. I'll use water as an example. Now, water has two very specific temperatures that we need to take into account. We have 0 degrees Celsius and 100 degrees Celsius. Now, as the temperature rises from negatives to about 0 degrees Celsius, water will be in the form of a solid called ice. When it reaches 0 degrees Celsius, it will go through a state change called melting. This will mean that the water will change from a solid to a liquid. Now, even though energy is used here, it's not used to increase the temperature, but rather to change the state. As the temperature increases beyond this point, water would be found as a liquid called water. It will then increase up to the temperature 100 degrees Celsius, where it will change a state again called evaporation. So now it will change from a liquid into a gas. So when the temperature increases above 100 degrees Celsius, water will be seen as a gas called water vapor. Next, let's have a look at neutralization. And neutralization is a chemical reaction. Now, when we work with the chemical reaction neutralization, we need to know the difference between an acid, a base, and a neutral compound. Now, on a pH scale, which is from 1 to 14, an acid can be found between the pHs of 1 and 6. A strong acid would be like 1, 2, and 3, and then a weak acid would probably be 4, 5, and 6. Then our base will be found on the other side of the pH scale. So strong base would be like 13, 14, and a weak base would be 8, 9. And right in the middle at 7 would be a neutral substance. Now, a neutralization is when an acid and a base is added together in certain quantities to produce a salt and water. For example, if we have hydrochloric acid with sodium hydroxide, we will get sodium chloride, our salt, and water. Okay, let's have a look at photosynthesis. And photosynthesis is a biological process. It's the process by which plants make potential chemical energy in the form of glucose. So plants use light energy that they get from the sun and then turn it into glucose as well as oxygen. Now, photosynthesis does occur in plants as well as photosynthetic algae and even some bacteria. Now, the balanced chemical reaction for photosynthesis that we need to know is 6 carbon dioxide molecules plus 6 water molecules will give us 1 glucose molecule, which is C6H12O6, and 6 oxygen molecules. Now we can have a look at reversible reactions, and in chemistry this is a whole chapter, but I'm going to try and sum it up as quickly as possible. Now, reversible reactions are reactions that can go in the forward direction as well as the reverse direction, meaning that our reactants will form products, but our products can also reform reactants. So I'm going to use the Haber process as an example. Now, the Haber process is basically where nitrogen gas plus hydrogen gas forms ammonia. But this is a reversible reaction, meaning ammonia can then decompose into nitrogen and hydrogen gas as well. So we indicate a reversible reaction by these 2 little arrows, showing both the forward reaction as well as the reverse reaction. Now, there's a few factors that we can change in this reaction setting that would either affect the speed of the reaction or the direction of the reaction. The first one's temperature. Now, the Haber process has a negative enthalpy, meaning that the forward reaction would be exothermic. So if I increase the reaction setting in this reaction, then my reaction would like to balance it out, meaning that it would favor the endothermic reaction to be able to absorb some of the heat and balance out the temperature. So the endothermic reaction would be the reverse reaction. So the reverse reaction would be favored. Now the opposite will happen if I decrease the temperature. If I decrease the temperature, the reaction would want to release energy or heat into the environment. So my exothermic reaction would be favored. Thus, my forward reaction will be favored. The second one that I can look at is concentration. So this one is pretty simple. If I increase the concentration of my reactants, they would obviously try and form more product. So the forward reaction will be favored. If I increase the concentration of my products, then more reactants will be formed. So my reverse reaction will be favored. Then we also have pressure. Now pressure only affects gases. So if I increase the pressure, my reaction would want to favor the side with the least amount of gas molecules. Now if I look at my reactants, I can count 1 nitrogen molecule and 3 hydrogen molecules. So in total, there's 4 gas molecules in my reactants. And in my products, there's only 2 gas molecules. Meaning that if I increase the pressure, my forward reaction would be favored as the product has the least amount of gas molecules. And of course, the opposite's true for decreasing the pressure. Then my reverse reaction would be favored because they have more gas molecules. Lastly, we need to know the effects of a catalyst. Now, catalyst will speed up the reaction, but it would not change the direction of the reaction because both the forward reaction as well as the reverse reaction would be increased or sped up the same amount. They then give us roasting. Now, roasting may sound similar to burning or combustion, but it's much different. Where combustion is the burning in air to produce carbon dioxide and water, and of course heat energy usually, roasting is when an ore or a metal is heated in the presence of oxygen to form a metal oxide. Now, roasting is usually used in the extraction of copper and zinc. Now, for copper iron sulfate, which is the ore, will be roasted in air to get rid of the sulfide ion. And the same with zinc. Zinc sulfide is roasted in air to get rid of the sulfur. Now, of course, we can then also use roasting for the formation of sulfur dioxide. And this will be done by the previous examples of roasting the sulfide ores. Lastly, we have thermal decomposition. Now, thermal decomposition is basically when a substance is broken down into smaller molecules through the use of heat. Now, a good example of this is the thermal decomposition of calcium carbonate. So if we heat up calcium carbonate, we will get calcium oxide and carbon dioxide. Now we can have a look at the questions. So they say answer the following questions about the processes A to H. Each letter may be used once, more than once, or not at all. State which of the processes A to H, meaning that they want the letter, not the name of the process. Now A asks, which one of these processes happens when an acid reacts with an alkali? Now remember, an alkali is just a base that's in aqueous form. So when I have an acid and a base, this would be a neutralization reaction. So the answer would be B. Next, they ask, which one of these processes reaches a position of equilibrium? Now the only process that can reach an equilibrium is a process that can have both the forward and the reverse reaction. So this would be a reversible reaction, or F. Then they ask which one involves particles changing from a fixed position to being mobile but still touching. Now fixed position refers to a solid, whereas mobile but touching refers to a liquid. Now when we go from a solid to liquid, we're melting a substance. So the answer would be C. Then they ask which one are physical changes. Now combustion would be a chemical change because we're producing new molecules called carbon dioxide and water. Diffusion would be a physical change because we're not changing the structure, we're only changing the state that the molecules are in. Melting is also a physical change because we're only changing the state that they're in. Neutralization is also a chemical reaction because we're producing new compounds like salt and water. Photosynthesis is also a chemical reaction because glucose and oxygen will be produced, which are new molecules. A reversible reaction is also a chemical reaction because new molecules are being produced. And then roasting and thermal decomposition is also chemical reactions because here we form oxides, so new molecules are being produced. So my answer here would be B and C, diffusion and melting. They then ask which is caused by gas particles colliding with each other. Now if we think back to our little lesson that we had before the question, we know that colliding with each other is a property of diffusion. So my answer here is B. Okay, let's go to the next page. Question 2. They state that this question is about the atomic structure and the periodic table. So just before we start with the questions, let's have a little look at the periodic table. So here's the periodic table that you will find at the back of your paper. Now when we look at our periodic table, we can see distinct periods. So here's period 1, 2, 3, 4, 5, 6, and 7. Now the period that an element's in also tells us how many shells for our electrons that element has. So let's look at lithium as an example. Lithium has a total of 3 electrons with a total of 2 shells. Now my first shell can have a maximum of 2 electrons, and my outer shell can have a maximum of 8 electrons. But this one only has 3 electrons, so my outer shell here would only have 1 electron. Now this outer shell electron, or the number of outer shell electrons, correspond with the group number. So group 1 will have 1, 2 will have 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, and group 8 will have 8 electrons in their outer shell. So now we know period is the amount of shells and groups is the amount of outer shell electrons. Let's look at lithium in a bit more detail. Now lithium has two little numbers next to it, a 3 and a 7. Now the bigger number on the atom would be the nucleon number. This is the amount of neutrons as well as protons in the nucleus. That's what's called the nucleon number. Now the smaller number is my proton number and only shows the amount of protons present in my nucleus. Now neither of these two numbers will tell me how many electrons I have, but I can deduce the amount of electrons by looking at the charge of the atom. Now this lithium does not have a charge, so it's neutral, meaning that my amount of protons needs to be equal to my amount of electrons. So it will have 3 electrons. Now if we look at a lithium atom that has 3 as a proton number, 7 as a nucleon number, and a positive charge, it means it will have 1 less electron than protons. This is because electrons give negative charges. So if I have 1 less electron, my overall charge would be positive. So here I would have 2 electrons because I have 3 protons. Now the last thing I need to be able to calculate is the number of neutrons. Now remember, my nucleon number gives me my number of protons plus neutrons, and my proton number only gives my proton number. So I can work out the number of neutrons by taking my nucleon number and minusing my proton number from it. So in the first example, and while in the second example, it would be 7 minus 3, which would give me 4 neutrons. Okay, let's get back to our periodic table. So now we understand the atoms and how to work out my protons, my neutrons, and my electrons. So now we need to be able to work out my electron configuration. Now if I look at my lithium atom again, I know my first shell has 2 electrons and my second shell has 1 electron, which means that my electron configuration would be 2, 1. Now this is pretty easy to work out if we draw the atom with all the electron shells, but in the exam we don't always have that time. So I'll show you guys another method. Now one way to remember it is by remembering that the first shell can have a maximum of 2 electrons and the second shell can have a maximum of 8 electrons. So if we look at phosphorus as an example, my first shell is my first period. So hydrogen and helium would be the 2 electrons. Then my second shell would be my second period. So that's 1, 2, 3, 4, 5, 6, 7, 8 electrons. And then my third shell, 1, 2, 3, 4, 5 to phosphor. So that's 5. So my electron configuration is 2, 8, 5. Let's do another one just to make sure we understand this. Let's take strontium as an example. First shell, 1, 2. Second shell, 1, 2, 3, 4, 5, 6, 7, 8. Then my third shell, 1, 2, 3, 4, 5, 6, 7, 8. And then my fourth shell, 1, 2, 3. So my electron configuration is 2883. Now this is pretty easy, but what if my atom is charged? Then the amount of electrons will differ from the amount of protons, so I cannot just count down the periodic table. Let's take oxygen for example, but let's make it a charged oxygen of 2 minus. This means that it has 2 more electrons than protons. So it means it will have the same electron configuration as the noble gas neon. So my first shell will have 1, 2. Second shell 1, 2, 3, 4, 5, 6. But then I have to add the 2 to get to neon. So 7, 8. So the electron configuration would be 2, 8. Let's do one more. Let's look at magnesium. But let's make magnesium charged to be magnesium 2 plus. Now this 2 plus means that it has 2 less electrons. So it will have the same electron configuration as neon again. So my first period would be 1, 2. My second period or shell would be 1, 2, 3, 4, 5, 6, 7, 8. And that is where I'm going to stop because I need 2 less electrons than a normal magnesium atom. So I'm not going to add that last 2 for the third shell. Okay, so now we can have a look at the questions. So the first question asks to define the nucleon number. Now we know that the nucleon number is the total number of protons and neutrons. They then ask us to state the connection between the number of occupied electron shells in an atom and the period number of that element. Now we know that the number of occupied electron shells will be the same as the period number for that element. C then asks to write the electron configuration for the atom and the ion. So let's go to our periodic table. Here we can see silicon. Now silicon is in period 4. So that would be 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4. So the electron configuration is 2, 8, 4. Then we need to find chlorine. But we know that this chloride is an ion. It's negatively charged, meaning that it has 1 extra electron. This means it will have the same electron configuration as argon. So in our first shell we have 1, 2. Second shell's 1, 2, 3, 4, 5, 6, 7, 8. And then in our third shell is 1, 2, 3, 4, 5, 6, 7, 8 electrons. So the electron configuration for the chlorine ion is 288. Next, they ask us to complete table 2.1. So this shows us the atom or the ion with the number of protons, the number of neutrons, and the number of electrons. So if we look at the first one, which is sodium, we can see that the smaller number 11 shows us the number of protons. Then, usually at the top on the right hand corner, it would give us a charge. Here it says nothing, so we can assume that this atom is neutral. That would mean that it would have the same number of electrons as protons, so 11. Now the number of neutrons can be calculated by taking the molecular mass, or the atomic mass in this case, which is 23, minusing the number of protons, and this would give us 12, which is the number of neutrons. So let's look at the next one, phosphorus. So we can see that the number of protons is 9 and it has a charge of -1, meaning that it would have 1 more electron than protons. So it would have 10 electrons. Now in the next one, they do not give us the atom or the ion, so we need to figure that out. Now we know that the number of protons is 31, so the bottom number would be 31. And then we also have the number of neutrons. So if we add the number of protons with the number of neutrons, so 31 plus 38, this would give us 69. That means that it would have an atomic mass of 69. So we can write that down. Then we can also work out the charge by working out the difference between the protons and the electrons. So if we take 31 minus 28, that would give us positive 3. So we would know that it has a 3 plus charge. The last part is to work out what the atom or ion is. Now to do this, we would look at the proton number. Remember, the number of electrons can change as the ion's charge changes. So we cannot look at the electrons. We can also not look at the neutrons because the neutrons can change between different isotopes of the same element. So we have to look at the proton number. Now we can see by the proton number and on the periodic table that this atom or this ion would be gallium. So on the next page we have question E. They say a sample of thallium contains two isotopes, 203 and 205. They then ask to define the term isotope. Now isotopes are atoms of the same element, but they have different amounts of neutrons, meaning that the amount of protons stay the same. The next question asks, the relative abundance of 203 thallium and 205 thallium is in the ratio of 3 to 7. Calculate the relative atomic mass of thallium in a sample to 1 decimal place. So the first thing we need to do is work out the total thallium. So this means we take 3 plus 7 and that would give us 10 in total. Then we can work it out. So we're going to take 203 thallium, so 203 multiplied by its fraction. So this would be 3 over 10, which is the total. And then we'll add the 205 thallium. So this would be 205 multiplied by its fraction, which is 7 over 10. This would give us a total of 204.4 for the relative atomic mass. They then asked to suggest why these two isotopes have identical chemical properties, and this is because of their electron configuration. So the way the electrons are configured around the nucleus of the atom will determine how it chemically reacts. This is because the electrons will be attracted to protons in other atoms, and depending on how they're situated, they might attract stronger or repel each other stronger. So if two elements have the same electron configuration, it means they would have the same chemical properties. Okay, let's move to the next question. Question 3. They say copper 2 sulfate has the formula of CuSO4. Now, aqueous copper 2 sulfate is a blue solution. A sample of aqueous copper 2 sulfate is made by adding excess copper 2 oxide, CuO, to hot dilute sulfuric acid, which is H2SO4. So before we continue with the rest of the question, let's have a look at how we can form different salts. So because this is an example of a soluble salt, we will go through the different types of methods to form soluble salt. So the first method is by mixing an acid to a metal, an insoluble base, or an insoluble carbonate, meaning that we'll add a liquid to a solid. The second method is to add an acid to an alkali, meaning that we'll be adding a liquid to a liquid. Let's go through the first method first. So we'll first need a beaker, and in our beaker we'll add our dilute acid. We will then heat up the acid to increase the rate of the reaction. We can then add our metal or our insoluble base or our insoluble carbonate. Now remember, even though the metal or the insoluble base or the insoluble carbonate is insoluble, it's insoluble in water and not in acid. So we can add it until it's in excess, meaning until nothing more is dissolving. We will then continue to heat it up and then pour it through filter paper to get rid of excess metal or insoluble base or insoluble carbonate. We will then pour the liquid that is left over into an evaporating basin. We can then heat it again until the point of crystallization. Now the point of crystallization is when tiny crystals start forming on the edge of the evaporating basin. We can then stop and then leave it to evaporate further. This will form crystals of the soluble salt. We can then decant the extra solution that's left and then blot the crystals dry using a paper towel. And there we go, our soluble salt crystals. Now let's have a look at method 2. We're also going to need a beaker. We're going to fill our beaker with our alkali and then also add an indicator. And the indicator is going to show us when our solution is neutral. We're then going to set up our titration apparatus. So that would include our burette. And inside of our burette would be our acid. We'll then titrate our acid into our alkali until our indicator shows that we found the point of neutralization, which we call the end point. We'll then take our neutral solution and add it to an evaporating basin. We can then heat up the liquid in our evaporating basin until the point of crystallization. So again, this is the point where tiny little crystals forms on the side of our basin. We will then again decant off the excess solution and then blot our crystals dry using a paper towel. And there we got our soluble salt. Let's get back to the question. So A asked, complete the symbol equation for the reaction, include state symbols. So our first one is copper oxide. Now copper oxide is a metal oxide, meaning that it's insoluble in water. So this would mean that it would be a solid. We then have sulfuric acid. And like we can see in the question, they say dilute sulfuric acid. Now the word dilute should indicate that it's aqueous. We then have copper sulfate. And in our question, it says that we produce aqueous copper sulfate. So we know that this one is also aqueous. Now when a metal oxide and an acid is mixed, it produces a salt as well as water. We can also determine this by looking at what already was formed. So we have copper sulfate as our product. We already have copper and sulfate as our reactants. What's left is an oxygen atom as well as 2 hydrogen atoms, which also shows that we form water. Question B then says state one observation which shows that copper 2 oxide is added in excess. Now, like we saw in the first method of our example, no more of the insoluble metal would dissolve into our solution. So we can state that no more copper oxide dissolves into the solution. Question C then asks to describe how aqueous copper 2 sulfate can be separated from the reaction mixture. Now remember, copper 2 sulfate is soluble, and the only other compound in the solution of copper 2 sulfate was excess copper 2 oxide. So it can be separated through filtration. D then says that crystals of hydrated copper 2 sulfate can be obtained from aqueous copper 2 sulfate from crystallization. They then ask to state what is meant by the term hydrated. Now, hydrated refers to it being a substance that is chemically combined with water, meaning that it's not dissolved into water like an aqueous solution, but that there's water molecules inside of the crystalline structure. They then asked to write the formula of hydrated copper 2 sulfate. Because they said formula, it means that they do not need the name equation. You need to give symbols. So this would be Cu for copper, SO4 for sulfate, and then a dot which means multiply, and then 5 water molecules. Lastly, they asked to describe how this crystallization is done. So this is done by heating the solution up to the crystallization point, otherwise called the saturation point. The solution is then allowed to cool. In question E, they say that aqueous copper 2 sulfate undergoes electrolysis using graphite electrodes. So let's quickly go through the basics of electrolysis. Now, all reactions of electrolysis has the same basic components. You'll have a beaker with two electrodes that are connected to a power supply. One of the electrodes will be a cathode, meaning that it is negatively charged, and one of the electrodes would be an anode, meaning that it is positively charged. Now, the movement of electrons will be from the anode towards the cathode and then through the electrolyte. Now, inside of the electrolyte, the substance that's dissolved into the solution will separate into its ions, positive ions as well as negative ions. Now, the positive ions, called cations, will be attracted to the cathode, and these will either be metals or hydrogen. Now, to determine what reaction takes place at the cathode, we would have to look at the reactivity series. Now, if this metal is less reactive than hydrogen, then it will react with the cathode. But if the metal is more reactive than hydrogen, then hydrogen will react with the cathode. Now, anions will be attracted to the anode, and these are usually nonmetals or hydroxide ions. Now, to understand what happens here, we need to look at the concentration of the electrolyte. Now, if a dilute concentration is used, then hydroxide will react, and if a concentrated electrolyte is used, then my nonmetals will react. Now, this is only true if my electrodes are non-reactive, meaning that they're made up of carbon. If my electrons are made up of a reactive metal, then something else will happen. At my cathode would be oxidized and dissolve into my solution. Now, if we had non-reactive electrodes, my solution would lose color because of the reaction. But if I use reactive electrodes, my electrode will dissolve into the solution and the color of the solution will stay constant. Now, at my other electrode, reduction would take place and the electrode will get a deposit onto it. Okay, so now if we look at our question again, they say that we're using graphite electrodes. We know that graphite's inert and won't react with the solution. They then ask to state why aqueous copper 2 sulfate conducts electricity. Now we know that copper 2 sulfate will be able to conduct electricity because it contains mobile ions. The second question asks to give two reasons why the electrodes are made up of graphite. We already know the first reason, the fact that graphite is inert. The second reason is that graphite will be able to conduct electricity. Then the third question asks to describe how the appearance of the electrolyte changes during the electrolysis of aqueous copper 2 sulfate. Aqueous copper 2 sulfate has a blue appearance. Graphite, being inert, will not react with the solution, meaning that copper 2 sulfate will lose its color and become a lighter blue. They then asked to describe what is seen at the cathode during the electrolysis of aqueous copper 2 sulfate. Now, copper 2 has a charge of 2+, meaning that it will be deposited at the cathode because it's the cation, positively charged. This means that the deposition would be a pink solid forming on the cathode. Then they're asked to write the ionic half equation for the reaction at the anode. Now remember, my anode is my positive electrode. So negative ions are going to be attracted to it. Now in my reaction, they did not state whether it was concentrated or dilute. So we can assume that it is a dilute substance. meaning that hydroxide will be attracted to the anode. So the reaction that we can expect here is 4 hydroxide ions forming 2 water molecules as well as oxygen. And then to balance it out, we add our 4 electrons. Now lastly, they asked to state 2 differences seen if the electrolysis is repeated using copper electrodes instead of graphite electrodes. Now remember, copper electrodes are a reactive metal, so it would also take part in the reaction. So the first thing that will occur is the color of the solution will stay constant. It will not go lighter. Secondly, one of the electrodes will dissolve, meaning that no bubbles will form. Question 4 then asks us some questions about oxidation numbers. So let's quickly go through the rules of our oxidation numbers. Now the first rule is that group 1 metals will always have an oxidation number of +1. Secondly, all group 2 metals will always have an oxidation number of +2. Hydrogen will always have an oxidation number of +1, except it will have an oxidation number of -1 if it is bonded to metals. Now fluoride will always have an oxidation number of -1, and oxygen will always have an oxidation number of -2, except when bonded to fluorine. And if it's bonded in hydrogen peroxide, then oxygen will have an oxidation number of -1. Now chloride will always have an oxidation number of -1 as well, but it also has an exception, and this is when it is bonded to fluorine or oxygen. So here they say that when magnesium nitrate is heated strongly, magnesium oxide is formed. The equation for this reaction is shown. So 2 magnesium nitrate gives us magnesium oxide plus nitrate plus oxygen. They then ask to state the change in oxidation number of nitrogen in this reaction. So, as our reactants, we can look at nitrate first. So oxygen has an oxidation number of -2, and there's 3 of them, so it has a total of -6. So overall, nitrate has an oxidation number of -1. So we can work out for X. -6 plus X, which is the oxidation number for nitrogen, should give us -1. That means that nitrogen oxidation number is +5. We then can look at nitrate or nitrogen dioxide as our product. Here, oxygen also will have an oxidation number of -2. There's 2 oxygens, so we have to multiply it by 2. Overall, nitrogen dioxide should have an oxidation number of 0. So we can work out for X again. Here, X would be +4. So my oxidation number will go from +5 to +4. The next question asks to identify the element which is oxidized in this reaction. Now for this, we need to remember oil rig. Oxidation is loss of electrons and reduction is gain of electrons. So let's first look at magnesium. We know that nitrate has an oxidation number of -1, and there's 2 of them, so magnesium will have an oxidation number of +2. Then magnesium oxide. Oxygen has an oxidation number of -2, the magnesium will have an oxidation number of +2. There's no gain or loss of electrons here, so it's not being oxidized or reduced. It's a spectator ion. Then we can go and look at nitrogen. And for this, we can actually just look at our previous answer. It went from +5 to +4, so it gained electrons, meaning it was reduced. So also not nitrogen. The only thing that's left is oxygen. Now in our reactants, oxygen has an oxidation number of -2. Then in our products, first In magnesium oxide, it has oxidation number of -2, so not there. In nitrogen dioxide, it has a oxidation number of -2. But then as oxygen, because it's standing alone, it will have an oxidation number of 0. So here it has lost electrons, meaning that it's oxidized. Our element being oxidized is oxygen. Our third question then asks to calculate the volume of nitrogen dioxide gas at RTP formed when 7.4 grams of magnesium nitrate is heated. So what we want is the volume of nitrogen dioxide, and what we have, or what is given, is the mass of magnesium nitrate. So we'll follow the steps. The first question says calculate the MR, so this would be the molecular mass of magnesium nitrate. Now this we can find on the periodic table. So we have 1 magnesium plus 2 nitrogen atoms plus 6 oxygen atoms. Now the atomic mass of magnesium is 24. The atomic mass of nitrogen is 14. And the atomic mass of oxygen is 16. Now when we add all of this together, we get a molecular mass of 148 grams per mole. Then they ask us to calculate the number of moles of magnesium nitrate that was used. So to calculate moles, we can say it's the mass divided by the molecular mass. Now our mass was given in the question as 7.40 grams. And our molecular mass is what we calculated in the previous question, 148. So if we divide 7.4 divided by 148, we get an answer of 0.05 moles. Then they ask to determine the number of moles of nitrogen dioxide that was formed. So here we're going to use our ratio. So we want the ratio of magnesium nitrate to nitrogen dioxide. Now magnesium nitrate was 2 moles and nitrogen dioxide was 4 moles. That's 2 to 4. Now we know that magnesium nitrate was 0.05, so I have to double it to get 0.1 mole of nitrogen dioxide. Then they ask us to calculate the volume of nitrogen dioxide gas in centimeter cubes at RTP. Now if you look at the back of your paper, you will see at the bottom of your periodic table, it does say that 1 mole of gas is 24 decimeter cubes of gas in volume. So you can work it out. We know that we have 0.1 mole. We can just multiply it by 24 to get 2.4 decimeter cubes of gas. But now we have to convert it to centimeters cubed. Now 1 decimeter is equal to 10 centimeter. But because these are cubed, we have to do it 3 times. So I'm gonna multiply by 10 to the power of 3. So 2.4 times 10 to the power of 3 would give me 2,400 centimeters cubed. Question B then asks us to do some dot and cross diagrams. So let's look at how we can do this for different compounds. Now there's 2 dot and cross diagrams that you need to be able to do. The first one is ionic bonding. Now ionic bonding happens when a metal and a non-metal bonds together. So these two have different charges and the electrostatic force between them will keep them together. Now we're going to use sodium chloride as an example. Now sodium is from group 1, meaning that it has a charge of 1 plus. This shows that it loses 1 electron. So when we draw the dot and cross diagram for ionic bonding, we will first create square brackets and put the charge at the top right corner of the square bracket. We'll then add the atom in the middle. So we know that in the first shell, sodium will have 2 electrons. Then in the second shell, sodium will have 8 electrons, and in its third shell, sodium will have 1 electron. Now this 1 electron will be removed as it loses 1 electron. We're then going to do chloride. Now chloride is in group 7, meaning that it has a charge of 1 minus, so it gains 1 electron. Again, we're going to start with our square brackets and our charge on the outside top right corner of the square bracket. We're then going to add chloride, the atom, and in its first shell it will have 2 electrons. Now here we need to use a different symbol than the first one we used. Now the first one we used dots, so the second one we're going to use crosses. Now the second shell it would have 8 electrons, and in its third shell it would have 7 electrons. Now that 1 electron from sodium will go to chloride, so this electron, the last 8th electron, will draw as a dot. Now we need to remember to read our question carefully. Sometimes they ask to only draw the outer shell of the electrons. Then we're not going to draw the shells in between. So it would look something like this. We draw sodium with the 1 plus charge, showing that it lost 1 electron. And then chloride will put in our square brackets with the outer shell of electrons, showing my 7 X's and my 1 dot from sodium. Now the second type of dot and cross diagram that we need to be able to do is covalent bonding. Now covalent bonding is between 2 nonmetals and they share electrons. So the drawing would look a bit different. We're going to use methane as an example. Now carbon is in group 4, meaning that it has 4 outer shell electrons. And hydrogen is in group 1, meaning that it has 1 outer shell electron. We will draw carbon in the center of our diagram and have a circle around it. This would be our outer shell for our electrons. We'll then add the 4 hydrogen shells around the carbon, and in each one will show our hydrogen. Now we need to decide which symbols we're going to use for which atom, and we don't want the same symbols to overlap. So for hydrogen, we're going to use X, and each hydrogen is going to have 1 electron. Then carbon has 4 electrons, so we're going to add 4 dots. Now we can see 2 electrons, so 1 cross and 1 dot would make 1 bond. Now we can go back to our question. They say magnesium oxide, MgO, is an ionic compound. Complete the dot and cross diagram in figure 4.1 of the ions of magnesium oxide. Give the charges on each of the ions. So we know that magnesium is in group 2, so it would have a charge of 2 plus. Now oxygen is in group 6, so it would have a charge of 2 minus, meaning that magnesium will lose 2 electrons to oxygen that would gain the 2 electrons. Now my second shell of electrons for oxygen would have 6 dots, as oxygen has 6 electrons in its outer shell, but then I would also add 2 crosses from the magnesium, giving 2 electrons to oxygen. Now magnesium will have a full outer shell of electrons, so 8 electrons. That is because the 2 electrons that it donated to oxygen would have been in the third shell that fell away. Now question C says oxygen is a covalent molecule. Complete the dot and cross diagram in figure 4.2 of a molecule of oxygen. The inner shells have been drawn. So we already know that oxygen is from group 6, which means that each oxygen would have 6 electrons in its outer shell. So let's start with the oxygen on the left. We're going to draw dots in a circular motion starting at the top. So 1, 2, 3, 4, 5, 6. And then on the crosses on the right, we're going to do the same. 1, 2, 3, 4, 5, 6. The problem here now is that each oxygen atom doesn't have 8 electrons in its outer shell. It has 7, which means something needs to change. And the only way I can change the covalent bond is by making it a double bond. So what we're going to do, starting with the dots, is we're going to add 2 dots in the space between the oxygens. Now, one thing that I have to remember here is to pair up my electrons because they're always in pairs. Now, with the crosses, we're going to do exactly the same. Now, if we count, each oxygen has 8 electrons in its outer shell, sharing 4 of the electrons. Okay, next page, question 5. Hydrogen is the first element of the periodic table. Hydrogen is used in fuel cells to produce electricity in vehicles. Now, the difference between hydrogen fuel cells and normal gasoline is gasoline undergoes combustion, whereas hydrogen undergoes electrolysis to form water. So they ask, name the substance which combines with hydrogen in a fuel cell. This would be oxygen, because hydrogen with oxygen will produce water. They then asked to give one advantage and one disadvantage of using fuel cells instead of gasoline in vehicle engines. Now, we know the problem with gasoline engines is that it produces carbon monoxide, which is poisonous and toxic to the environment. Now, the advantage of using water or hydrogen instead of gasoline is that only water is produced, so no carbon dioxide and no carbon monoxide. Now, disadvantage of hydrogen cells is that hydrogen needs to be stored at very high pressure. This can be dangerous and very difficult. There's also less hydrogen filling stations available, making it difficult for the consumer to use. Question B then asks, hydrogen gas can be made from petroleum by a 2-step process. So in step 1, petroleum is separated into different components. And step 2 is that large molecules obtained in step 1 are then converted into smaller molecules, including hydrogen gas. Now, the first question asks, name the process used in step 1. Now, step 1 is a good example of fractional distillation, where different sized compounds are separated. The second question then asks to name the process used in step 2. So here, large molecules obtained in step 1 are converted to smaller molecules. So this is called cracking. Question C then says organic compounds contain hydrogen atoms. Calculate the number of hydrogen atoms in 44 grams of ester methyl propanoate. So this is an example of stoichiometry. So let's quickly go through the basic steps that we will use. We're going to use the example of butanol, which is an alcohol. So the structural formula for this compound is CH3, CH2, CHOH, CH3. So we're going to say that there was 148 grams of this compound, and we need to calculate the amount of carbon atoms that are present in this molecule. So here we can see the displayed formula of the alcohol so that we can see exactly how many atoms there are of each. So we're going to use our usual method. So we're going to go from grams to mole, and then mole to mole, and then mole to atoms. Now, to go from grams to mole, we use the equation of mole is equal to mass over molecular mass. And then from mole to atoms, we're going to multiply it by Avogadro's constant, which is 6.02 times 10 to the power of 23. Now, the first part of my equation is what we have, and the second part is what we want. So we're going to start with the first part. What we have is the mass of our alcohol. So our mass would be 148, and now we have to calculate our molecular mass. So we have 4 carbons, 10 hydrogens, and 1 oxygen. So it's going to be 4 times 12 plus 10 plus 16, and that's going to give us 74. We're then going to divide 148 by 74, and this would give us 2 moles of our alcohol. We're then going to do step 2, which is our mole-mole ratio. So this is where we move between what we have and what we want. So we're going to take the ratio of our alcohol to the ratio of carbon moles. So we have 1 mole of our alcohol. Inside of our alcohol, we have 4 carbon molecules or 4 carbon atoms. So it's going to be a ratio of 1 to 4. Now we calculated the actual moles of our alcohol as 2. So we're going to double it and get 8 moles of carbon. We're then going to move to step 3, where we go from moles to atoms. So we're going to take our 8 moles and multiply it by Avogadro's constant of 6.02 times 10 to the power of 23. This is going to give us a total amount of atoms of 4.82 times 10 to the power of 24. So now we can start with our actual question. So we have 44 grams of ester methyl propanoate. 1 mole of ester methyl propanoate contains 6 times 0.2 times 10 to the power 23 molecules. So we're going to start with our first step and work out the molecular mass of this ester methyl propanoate. So we can see that we have 4 carbon molecules as well as 8 hydrogen atoms and 2 oxygen atoms. So we're going to multiply our 4 by 12. Then we're going to add 8 times 1. And lastly, we're going to add 2 times 16. And this will give us a total molecular mass of 88. Now we can work out the amount of moles of ester methyl propanoate. So we know that moles is mass over molecular mass. Our mass was 44 and our molecular mass 88. So if we divide 44 by 88, we get a mole of 0.5 moles of ester methyl propanoate. We're then going to go to our ratio. So our ratio of ester methyl propanoate to the amount of hydrogen atoms. So for 1 mole of ester methyl propanoate, I have 8 moles of hydrogen. So I'm going to multiply my 0.5 by 8. And this will give me 4 moles of hydrogen. I'm then going to multiply by my 4 moles of hydrogen by my Avogadro's constant, which is 6.02 times 10 to the power of 23. And that would give me a total amount of hydrogen atoms of 2.408 times 10 to the power of 24, which will then be my answer. So in our next question, question D, they say for each of the homologous series shown, name a member that contains 6 hydrogen atoms. Now the first one that they're showing us is alkanes. Now we can work out this answer by looking at the general formula. The alkanes have the general formula of CnH2n plus 2. So we need a total of 6 hydrogen atoms, meaning that we will have a total of 2 carbon atoms. So our answer would be ethane. The next one is alkenes, and they have a general formula of CnH2n, meaning that if I need 6 hydrogen atoms, I'm going to need 3 carbons. So here we'll have propene. Then we have alcohols with the general formula of CnH2n plus 1 and then OH. So here we have to take into account that there's 2 parts of hydrogen. So to have 6 hydrogens, we need 2 carbons. So we'll have an ethanol. Then lastly, we have carboxylic acids. And the general formula of carboxylic acids is CnH2n plus 1 and then COOH. So to have a total amount of 6 hydrogens, we're going to need 2 carbons. Now remember, we have the 2 carbons here and the carbon in our COOH. So this will be propanoic acid, as there's 3 carbons in total. Then question E says unsaturated alkenes are converted into saturated alkanes by a reaction with hydrogen gas. They ask us to state why alkenes and alkanes are hydrocarbons. Now remember, hydrocarbons are molecules that only contain carbon and hydrogen. Then they're asked to state why alkenes are unsaturated. Now, the reason why they're unsaturated is because they contain carbon-carbon double bonds. Now, it's important to refer to carbon here and not just double bonds, because some molecules can have a double bond oxygen and still be saturated. Thirdly, they ask, name the catalyst needed to convert alkenes into alkanes. So for this reaction, we would need a nickel catalyst. Then lastly, they ask to explain why the conversion of alkenes to alkanes is an addition reaction. And to answer this, let's quickly go through our organic molecule reactions. The first reaction we're looking at is an addition reaction. An addition means adding something to the molecule. So we're going to use ethene as an example. Ethene has a double bond, meaning that we can add hydrogen gas to the molecule to produce an alkane called ethane. So here the double bond is broken and 2 hydrogen molecules are added. The second reaction is a substitution reaction. So we are substituting some of the atoms for new atoms. So here we'll take our alkane or our ethane as an example and we'll add chlorine gas. When this is done, one of the hydrogen atoms will be substituted by chlorine and it will produce a halogenoalkane and hydrochloric gas. Lastly, we'll look at an elimination reaction. And again, we'll use an alkane, ethane, as an example. So in an elimination reaction, we take away some of the atoms. So in this reaction, we will take away 2 hydrogen atoms to produce a double bond alkene called ethene. This will also produce hydrogen gas. Now we can see in the addition reaction, we only produce one product, whereas in substitution and elimination, 2 products are formed. So if we go back to our question, where they asked to explain why the conversion of alkenes to alkanes is an addition reaction, it is because only one product is formed in this reaction. Okay, we can then move on to question 6. So question 6 says that natural polyamides are polymers made from amino acid monomers. Now remember that polymerization can be done in 2 different ways, either addition polymerization that has to do with alkenes, or through condensation polymerization that creates biological molecules. The first question asks to state the type of polymerization reaction that occurs when natural polyamides form, and this is called condensation. Then they ask to state the term given to natural polyamides, and this is called proteins. Now they say an amino acid is represented as shown. They then ask to complete figure 6.2 to show the general structure of an amino acid. We have to show all the atoms and the bonds in the functional groups. So if we go back to figure 6.1, this little block here will represent a carbon. Now attached to this carbon would also be a hydrogen as well as an R group. And the R group will represent the rest of the molecule. This is the part of the molecule that can differ between the amino acids. So we can redraw this in figure 6.2 by adding my nitrogen with its 2 hydrogen atoms, then also my R group, which isn't represented yet, and then my carboxyl, which is my carbon with my hydrogen, and my O and H atoms. Then in question D, they say 3 different amino acids are represented as shown. So here we have amino acid A, B, and C, and they all look the same except that they have different colored blocks. They then asked to complete the diagram in figure 6.4 to show the part of the structure of the natural polyamide that forms when 3 amino acids A, B, and C combine. Show all of the atoms and all of the bonds in the linkages. So if we go to figure 6.3 above, we need to remember that it's a condensation reaction that occurs. This means that water will be released. So we can go and look at the OH from amino acid A, as well as one of the hydrogens from amino acid B will be used to form H2O, meaning that we are left with a CO from amino acid A and an NH from amino acid B. So this means that these will bond kind of like this. Now remember, this will also happen to the other side of amino acid A where it loses one hydrogen, and also the other side of amino acid B where it loses an OH, and then the same for amino acid C. So we can then go draw the bonds into figure 6.4. So I have my nitrogen with my hydrogen, and I'm not going to add second hydrogen here because it's lost to water when it polymerizes. Then in between amino acid A and B, I'll have my carbon double bond O with my nitrogen and my hydrogen bonded to amino acid B. And the exact same thing between amino acid B and amino acid C. Then they say a mixture of 3 amino acids A, B, and C can be separated and the amino acids identified using paper chromatography. Okay, so let's quickly go through the basics of chromatography. So when we do chromatography, we always start with a solvent. Now the solvent in our example will be water, but this could be any type of substance. Sometimes even chloroform is used. So chromatography paper will be placed into the solvent. Now on the chromatography paper, there would be a pencil line drawn just above the level of the solvent. This is to show where we add our compounds that we want to separate. Our solvent will then be pulled up by the chromatography paper up to a point. We would then mark this point as well because we need to be able to work out the distance between these points. We can then add a locating agent. This will make it possible for us to see how our compounds separated. Now the compound that moved the least will probably be larger, less soluble compounds, and the compounds that move the most is smaller soluble compounds. We then need to work out our RF value. So we will calculate the distance that the solvent moved as well as the distance that our molecule moved. And we'll divide the distance our molecule moved by the movement of the solvent. This value will be able to identify our molecule, but it's not always very accurate. And it differs between the different types of solvents that's used. So on our first question, they ask us to complete the equation for RF. So this would be the distance traveled by the substance divided by the distance traveled by our solvent. Then we have question F. They say a sample of the mixture of the 3 amino acids A, B, and C is placed onto the baseline and a chromatogram is allowed to develop as shown in figure 6.5. The amino acids A, B, and C are colorless. Water is used as a solvent. They then also explain why the baseline is drawn in pencil. Now the reason why we draw it in pencil is because pencil is insoluble in water and won't be able to be drawn up with the solvent. They then ask to state the type of substance used to make the colorless amino acids visible on the chromatogram. Now this is called a locating agent. Then they ask to explain why in figure 6.6 only 2 spots are seen from the mixture of 3 amino acids. Now the reason for this is that 2 of the amino acids will have the same RF value, so they would have moved the same distance in the same solvent of water. Lastly, they asked to suggest how the experiment can be changed to separate the 3 amino acids completely. Now we can do this by using a different solvent. This will make the three amino acids move different distances and can be separated like that.